Okay, the next speaker is Ryuji Yoshida from YNU. The title is Development of a Seeding Method for the Typhoon Weakening based on the laboratory and the numerical simulation experiments.
So thank you very much. Sorry. Thank you very much, Chairman. My name is Ryuji Yoshida from Yokohama National University. Today, I would like to talk about the development of a seeding method for the typhoon weakening based on the laboratory and the numerical simulation experiments. So, as Professor Furias, introduced about the moonshot goal weight yesterday morning, we are tackling to a kind of the impossible mission. That is the typhoon controlling. So since we have already experienced the intensified tropical cyclones, and so we now suffering the huge natural disaster due to that such intensified tropical cyclones. So the one idea to reduce the risk is the typhoon weakening. So various methods from the various aspects of the typhoon mechanisms are proposed in our moonshot programs. Our group is addressing to an intervention in a crowd physics process by seeding impact materials from the aircraft. But a physical understanding about the microphysics and the different aerosol conditions in the tropical cyclones are not yet well understood. So we need to start from there. So the one possible mechanism is proposed by the Rosenfeld 2012. So the seeding with hygroscopic aerosol at the outer region will increase the number of the cloud droplets. Smaller size of the cloud droplets will be transported to the upper layer, instead making the rain droplet instantaneously local rain. So facilitating the diabatic heating in the upper layer by promoting the immigration of the cumulonimbus instead of the cumulus. So eventually the convergence related to this, the cumulonimbus at the outer area of the tropical cyclone will reduce the amount of the water vapor transport into the tropical cyclone. This will weaken the convection at the eye wall. So this is the conceptual model of the aerosol impact in the tropical cyclone. We do not have much confidence on this concept yet, but we will start our study from this concept. So we need to think about the estimation of the seeding materials to realize our operation realistically. So here I'd like to give a rough estimation of the required amount of seeding particles. Left-hand side image is an operation image. Let me assume that deploying the seeding over the torus-shaped region, these pink areas, the depth is all the way to the 10 kilometer. And 0.1 micrometer diameter of the NSCR particle will be used, and increase the number concentration up to the 1,000 cubic per centimeter. By expecting this one, the estimated amount is roughly 600 tons of the solid particles. This is corresponding to the roughly 30 of the CT transporter airplane. It might be possible. I don't know for sure, but obviously it's tremendous amount of the solids. So the basic studies are needed to increase efficiency and reduce the amount of the particles. So our purpose is study the possibility, show the possibility of the weakening by seeding. For this one, we are now addressing two major issues. One is understanding whether artificial aerosol act at the cloud and ice nuclei as expected under the tropic air condition. Because we have some kind of the experiences for the seeding in the mid-latitudinal condition, but we don't know about the details for the tropics air conditions. So we are now to try to doing the laboratory experiment for this point. And the second is understanding intensity change of the tropical cyclone when cloud droplet number is changed. So for this one, we are now running for the numerical simulations to investigate the sensitivity to the tropical cyclones changing by the cloud droplets in a model. Here I'm showing the chamber experiment. The left-hand side photo is a main chamber of this system. This is operated by the JMRI. And the right-hand side is an overview of the system structure. So it's much complicated system, so I will skip the detailed explanation for this one, but I will give you the simple idea of this laboratory experiment. So let me assume there is an air parcel, including the water vapor and the aerosols. This is lifted up by some local convergence. So then you can have you will observe that some cloud droplets are generated due to the adiabatic expansion cooling as the parcel is lifted. This laboratory experiment mimics this kind of the process. First, the air at a temperature and a humidity is injected in this chamber, and also the aerosols, artificial aerosols are injected into this chamber. Then, oh my gosh. Then the compression is applied for this chamber. So the reducing the adiabatic reproduce the adiabatic expansion process associated with the air parcel lifting is so reproduced inside of this chamber, and we can measure the cloud nucleation and the ice crystal nucleations. We can change the initial condition of the air inside this chamber, the more humid or more higher temperature, or we can change the particle size or the particle number of the aerosol, so we can check the efficiency of our artificial aerosols. So I expected to show you some preliminary results from this laboratory experiment, but I'm sorry, unfortunately, I can't show you an actual experiment result today. Because this system is originally designed for the mid-latitudinal atmosphere condition. So we found some problems when we applied for the tropics condition. So mid-latitudinal air is more drier and lower temperature, comparing to the tropical condition. So if we set the more humid, higher temperature, we found that some condensation inside the pipes of the systems. It's pretty big problem for explanation in this kind of the chamber system. So we now the chamber system is undergoing for the upgrade to achieve the tropics air condition. We found the right-hand side image. This is showing the relationship between the aerosol number concentration and the cloud particle size by changing the artificial aerosol size or the numbers. So I think that through this measurement, efficiency of the artificial aerosol can be evaluated in the near future. Okay, so let's move on to the simulation part. We now simulating the real case of the tropical cyclones. This year, I'm showing the typhoon Faxai in 2019 case. We used the CRESS-4i CCL model developed in Nagoya University, and we aim to understand the TC responses through the microphysical processes when cloud droplet number is changed. So here, in this time, we changed the number of the CCN ranging from the 50 to the 10,000. Then the calculated number of the cloud droplets is found from 50 to the 2,200. Okay, so we tested 6 cases by changing the number of the CCN. Then please note, this time, this constant, the CCN is valid uniformly whole the computational domain. So no special structure is given for the number of the CCN. So here I'm showing the simulation result. Left-hand side is the temporal evolution of the central pressure for the different setting of the number of CCN. And the right-hand side is showing for the difference from the number of the concentration of 50, in most green case. So you can see that the difference for these cases. So please see the brown lines. This is NC 2200, the most polluted one, assuming the polluted case. This shows almost always the weakening. So here the positive value means a weakening comparing to the NC50. So the weakening amount is up to the 2 hectopascal in the maximum sense. So it's good for, but if you see the moderate number of the NC, for example, the 200 or the 900, you can see the part of the time for the simulated time, the intensification is found observed in some cases. So it's implied that operation of this kind of the intervention is pretty difficult. Here showing the vertical radius cross section to check some kind of the consistency with the Rosenfeld hypothesis. Upper row is vertical speed and the bottom row is the total hydrometers. This is the 600 hours temporal mean and also the dimensional mean is applied. On the left is a small number for the NCs, and on the right is a large number of the NCs. So you can see that some kind of the immigration of the convection can be found in a bit out area of the total cyclones. So it seems to be consistent with the Rosenfeld hypothesis. So to study the difference in sensitivity by case, we conducted a similar numerical simulation for the different typhoon case. Here I'm showing the Typhoon Hagibis case. This is a much bigger tropical cyclone case compared to the previous one. Left-hand side figure showing the difference from the 200 NC 200. Here I'm showing the 900 and the 1600. So the same stories can be found. So in this case, you can see the almost always weakening, whether at NC 900, 1600. So it's good news for us. But the weakening is about 0.4 hectopascal, and in the maximum sense, it's 1 hectopascal. So it's much weaker than the previous one. So we need to check more. And here I'm showing the vertical radius cross sections. The left-hand side is a small NC number, and the right-hand side is large NC number. You can see some kind of the higher number of the total hydrometers, a higher value for the total hydrometers in large NC case. But you can see that also there's a similar response inside of the tropical cyclones because we studied the difference of the NC number for whole computational domain. So we need to check the more limited areas necessary. Here I'd like to wrap up my talk. So we're now going on the moonshot project, and our project is studying typhoon weakening method from the intervening in cloud microphysical processes. And so far, we found some real-scale simulations with large NC number tend to have the higher central pressure than small NC numbers. And also, we now try to idealize the simulation to understand the digital processes in the microphysics of the tropical cyclones in simpler conditions. All right, that's all what I have today. Thank you very much.
Are there any comments or questions? Can you show us the temporal evolution of central pressure in a numerical simulation? Previous one.
Previous one, okay.
Yeah, this one. Yeah, they are fluctuate irregularly. Is that correct?
Yes.
Not linearly.
Not
change.
linearly. Yeah. So yeah, if you see this left-hand side one, you can see that you can't find the linear reactions, linear torrent by changing this NC numbers. So it's pretty difficult for, But maybe we found some kind of the good response by changing the areas or the timing for the increasing of the NC numbers.
I see. Thank you. It also.
Okay. Yeah.
Okay, it's time. Thank you very much, Yoshida.
Thanks so much.